left EcoStep behind and rebuilt their own version of EcoStep.
Okay, I think you're on.
Yeah, obviously Andrew was the initiator of that move, which is really cool.
His partner, Bill Frank, what do you call him? I think did a lot of the coding, but she she had a degree in computing. So
What was his background?
he was an architect, yeah.
Oh, okay. It's going to plague me until someone goes Andrew EcoStep.
Oh yeah, I'll be able to look at it in a sec.
Bill Downey was a Jennifer. I can't remember what
Yeah, you're up and running. That's great. Yep. His name is Andrew.
I can't even picture him. I never met him face to face, but we had a few Skype sessions. It's very early days, because it was like, oh, well, there's a guy that's sort of successful in creating some modeling software.
Andrew
Marsh.
Jesus, close.
More Marsh. Yeah, I was pretty.
So we're going to talk about decarbonising grids. I guess one of the interesting things about life cycle assessments is that it's for the life cycle of the building, so it's fairly easy to see what it's going to do over the next year, but to say what it's going to do over the life cycle, its entire life cycle of 50 or 100 years, gets a bit more challenging. So what I'll talk about is how likely we think at the moment that the grid is going to decarbonise, how eTool can tackle this in the modelling, and how it affects our life cycle design decisions. And then we can throw up at the end and see if we think we're doing it right. So will the grid decarbonise? There's a lot of depressing things that you see in the media at the moment. That's me not very happy. You've got things like taxing of the renewable energy target, the carbon tax, etc., etc. Especially with the current government, it's quite easy to get depressed. But on the other hand, you've got, well, actually, this trend is also fairly depressing. If you go back to 1990, this is the carbon intensity of the grid, grams per kilowatt hour, and it's sort of trending upwards over the last 10 years with dips and troughs. It's not as depressing as it quite looks, probably, because at the same time you've had a massive increase in the demand for electricity as well.
So that's total emissions, not intensity per.
No, that's intensity per unit.
Oh, is it?
Yeah.
Right.
Yeah. Intensity per, sorry, say that again?
Per kilowatt hour.
Oh, okay.
So why did the intensity go up?
Is that Australia, over the whole of Australia?
That's Australia average, yeah, since 1990.
No, I reckon probably because snowy hydro has become less and less.
Dominant feature of
it used to be 15% of the NEM, I think. Yeah. Maybe in 1996, I'm pretty sure it's 15%.
So we stopped building hydro and picked up more coal.
Well,
must have been.
the other side of that is, of course, there's not a lot of places that are getting built like.
Oh yeah, of course, and also it hasn't been as much rain as well.
Yeah, okay.
Yeah.
So
yeah.
I mean, you've basically got the hydro stations in Tasmania, and you've got the snowy river scheme, and a little bit up in Kununurra, and that's basically.
Yeah, there's one here down at Serpentine.
No more interruptions.
I forget your video. So.
Yeah, although this is 2009, so go on for the last 5 years, and I think it's kind of flatlined over the last 5 years. It hasn't. We're sitting at about a gram per unit at the moment. So there's some things that make us happy as well. Like this is the falling cost in PV over the last 5 years even, and it's more than halved over the last 5 years, becoming a lot more prevalent, a lot more people putting solar panels on their roofs, creating a lot more renewables that are going into the grid. Wind is doing something similar worldwide, although not so much maybe in Australia, but worldwide the price of wind projects is coming down. Even China is getting on board and investing pretty heavily in renewables. So feels like the balance is tipping in favour of renewables, and we're heading in the right direction. In any case, Australia is still bound to its Kyoto target at the moment, which is an 80% reduction in CO2 on 1990 levels. So something like that would track this sort of direction down towards 2050. The blue line assumes that you wait a little while and then you hit it hard, and then to make up for the stuff that you emitted early on, then you have to drop off a bit further as you get down to the end, and the dark blue line is a more linear kind of trend towards that target. So what eTool have done is assume that electricity emissions are going to follow this kind of trend as well, so a kind of linear trend towards 80% reduction in emissions from electricity by 2050. So this table, what that looks like is in 2013, on the left here we have the efficiencies of all the generators at the moment, and then on the right column,
pointer, so we can see that on the screen. What you're pointing at.
Yeah. So on the left we have efficiencies here, and on the right this is the contribution that it's currently making to the grid. So you can see solar PV is still very low at 0.1%, a bit of hydro, and predominantly coal and gas. And if we were to trend that towards an 80% reduction to 2050 here, then we can get a 50% input from gas, a bit of renewables, and a fair bit of wind, and we're at that 80% target. The table in the middle is the kind of midway point, so what it would look like halfway through in 2030.
That includes growth.
No, it doesn't. It's just straight percentages.
Yeah, just straight percentage.
Assumes that energy efficiency would, and it's actually only looking at fuel decarbonisation of fuel. Yeah. So there's definitely limitations to it. If demand grows, then you have to decarbonise harder than that. But at the moment, demand for electricity is actually falling. So who knows whether that's going to continue. But and the other point about this is potentially you would have to decarbonise other areas of the economy more, because they would be harder to decarbonise. So the grid may actually be easier to decarbonise, so this might have to actually decarbonise more than what we've modelled. But we're just running this rough scenario to get a feel for what it does.
It's interesting you've got shown there that brown coal will decarbonise to 0%. I don't think that's true.
I think that's use of coal.
Yeah, just use of it. Yeah.
No coal.
Yeah, but understand that the coal-fired power stations in WA are all brown coal, they're not black coal. So you're going to wind up with all this dirty. And the Pinjarra power station doesn't even have scrubbers on it to get rid of the grid. So they ain't going to put you.
This is assuming that if we were to hit this target, we would have to basically cut the coal out. Yeah. So whether we hit it or not, that's, I guess, up for grabs. But if we hit it, this is what we'd have to do. Well, this is one scenario.
Yeah, it's one scenario. It's probably the easiest one. Like, if you had a bit more coal on, then you're going to have a lot more renewables to kind of make up for it.
And actually, I'm surprised at how easy that would be to hit. Like, it's still 50% gas. Like, that's the other thing, that it's combined cycle. It's higher efficiency gas, but I actually thought it would have been. I thought it would have been more like 30% gas at the most. So 80% reduction is actually, you model very easily achieved.
I mean, you're only growing solar to 7.5.
Yeah, exactly. This is not, and you're not even really talking about. I don't think it's all that hard. Yeah, basically.
I'd go along with you. I think it's effective.
Yeah.
We could just about be a total solar country without having any coal.
Yeah.
Mm. Australia's got this massive advantage of starting from such a bad spot. Like if you're in Europe where you're already starting at 0.5 of a kilogram per unit, and you've got to get 80% reduction on that, then you're starting to get into some real sort of challenges. But, yeah, you're already twice as bad as Europe, so moving down to 8% is relatively easy from that point of view. So that's the trend again. This is what it's doing to your kilograms of carbon per unit of electricity. It's starting off at around 1, and we're aiming for around 0.2 in 2050. So how does that look when we model it? Basically, these are 3 models. One is the current grid intensity. So we have 25% of our emissions are tied up in all the materials and construction that's gone into the building. 11% is in recurring impacts, so replacing the carpet, the paints, and etc. And 64% is in your operational electricity and gas and operational energy. When you get to 2050, it's starting to even out a lot more. Your emissions intensity of your electricity has dropped so much that your materials are taking up a much bigger chunk of your life cycle emissions. What's interesting here though still is that we're looking at, this is an average building in average residential house in WA, and we're still looking at 2.5 tons per person per year. We're trying to get down to the sort of 1 ton target that we've been talking about. Still a lot of work to do with that kind of renewable grid. And this is what it does to the design decisions. So I've just taken a couple of kind of standard recommendations that we tend to look at. One is going from an electric instantaneous hot water to gas. One is improving the efficiency of your air conditioner. One is PV system on your roof, and then we have the materials impact, so using fly ash in your concrete or replacing your carpet with timber floor. And so we tend to focus on the energy side at the moment because our current assumption is that we have this 2013 grid and we apply it over the life cycle of the building. That's kind of what we do in our work at the moment, and we focus definitely on this operational side, and you can see you're getting some big savings there. But when you look at the 2050 grid, these savings are not nearly as big. In fact, going from electric instantaneous to gas increases your emissions, because although the gas grid and the 2050 grid are fairly similar, around about 0.2 kilograms, your efficiency of your gas boiler is a bit worse, so you're actually increasing emissions. And then your electric efficiency measure for your air conditioner is quite a small impact, and things like fly ash and the carpet is a lot bigger focus to put your money on.
Why did fly ash and carpet increase, as you say?
They haven't. They've stayed the same.
Oh, well, that's quite an optical illusion, isn't it? Interesting.
Yeah, you change
just
colours.
compared to the
Yeah, it was not even looking at it. In my eyes, it actually looked bigger.
Yeah, they're the same.
That's quite interesting.
And you also, your impact from your PV has gone down a bit, and in fact, if the grid continued to decarbonise in Australia very rapidly, and the PV was coming from China that maybe wasn't decarbonising at all, then you would get to a point where the materials that have gone into the PV aren't actually being recouped in the savings, the operational savings. And that's the 2030 grid, so it's sort of halfway between. The 2030 grid would be the average, if you took the life cycle of the building, the 2030 grid is the average grid intensity from now until 2050. The 2050 grid is imagining that you're building a building in 2050. 2030 grid, I guess, is a kind of average grid intensity over the next 50 years. That's a good scenario for you to look at.
I think this is really interesting, Pat. So I've got a couple of questions. So the first one is, That's swapping an a gas hot water system with an swapping an electric instantaneous with gas hot water system. So from moving from electric to gas.
Yeah.
And is it gas storage?
Gas instantaneous as well. I think. Yeah.
Electric instantaneous to gas instantaneous.
Yeah.
So if your building was going to last 100 years, you'd want to be able to retrofit it. You'd probably still install the gas now, but you want to be able to retrofit it with electric. Is that right?
Yeah, that's the recommendation that we kind of put forward, and keep our fingers crossed that in 20 years' time someone will be smart enough to do that, or that the price of gas or carbon tax or whatever that comes in properly by then will make people make that change. Yeah.
And the second one's a high efficiency aircon. That makes sense. The third one is installing PV. Okay, that makes sense. And then the last fly ash. Just explain that to me.
So we have fly ash concrete, which is replacing a proportion of the concrete that's gone into the building with waste product at the moment, fly ash from steelworks. So this is during the construction of the building, you've reduced your impacts from your concrete, and that's locked in for the life cycle of the building. It's like one hit, as it were, when you build the build. And
carpet, is that like a sustainable carpet or an eco carpet?
The carpet is replaced with a timber floor.
Timber floor, okay.
Yeah.
Yeah. Cool.
Sorry, the carpet's replaced with timber?
Timber, yeah.
Yeah, so you get a benefit moving in that direction, yeah.
Replace or is not putting in carpet because you just already used the floor you've got?
Oh, it's like a nice laminate kind of timber floor that I put in. But whereas you would replace a carpet every 10 years, a timber floor would probably last 20 or 30 years.
It's interesting that concrete. I thought the concrete had a bigger impact on that.
This is for like a single-story residential house, so there's actually just a bit of concrete in the slab, maybe a bit in the foundations. But it's not massive. Yeah.
The other thing is there's still impacts that relate to the reinforcement and all those other factors. So all you're doing is replacing a portion of the Portland cement with fly ash. Yeah.
Yes, understand what you're getting at. There is another cement product in my company that's called that, but it's the old Roman style cement. It takes about 3 or 4 times longer to go off. Anyway, so if you poured a concrete slab, it will probably take 3 or 4 weeks off.
Yeah.
But because it's not fired like it is with Portland cement, there's no embodied energy in that.
Okay.
A hell of a lot less embodied energy. And it becomes almost as strong, like 85 to 90% strength of Portland concrete.
Yeah.
I can't remember what it's called.
I'm going to hit you up about that, Ian. So yeah.
But as I say, the concrete would have been fairly heavy on the embodied energy.
It is heavy, yeah. So this is a table here of the top materials impacts in the kind of standard residential house, and concrete is at number 1. It's got definitely the largest embodied impact. So what we have split out here is you've got the initial impacts from the construction, first hit of the construction. You've got transport, so transporting the materials to the site, and then you've got recurring impacts, so the things that need replacing over the life cycle of the building. There's also recycling credits and impacts from waste when the building's demolished. So the initial impacts, these are the things that we can lock in now. So if we're looking at those future grid scenarios, these are definitely things that we would look at. The recurring impacts are things that we have not really looked at modelling yet, but there is also, as the grid decarbonises, the hope is that the whole economy will also decarbonise, and replacing something like your carpet or your paint will also have a linearly lower impact than it does at the moment. So something else that we would like to consider, and maybe we might look to considering in the future, but Yeah, at the moment, the focus is, if we're looking at the future grid scenarios, the focus should be on these initial impacts rather than recurring ones. There's other future scenario that we might want to look at is what's going to happen to the gas grid. It's already fairly low, but there are technologies out there and people doing things that are reducing the impacts associated with gas. So you've got landfill gas collection, you've got cow poo collection from anaerobic digestion, and
slightly more technical.
and you can even go really basic, and like people have been doing this for hundreds of years, is collecting their food waste and animal waste and use the gas off that just straight away for cooking kind of needs. So that's all things that might happen to the gas grid as well that we haven't sort of tackled yet at eTool, but may look to soon. There's other impacts that are also fairly likely to happen. This is from the Garner Institute, saying that assuming a 2-degree rise, which is almost locked in now, I think we're at 1.5 degree rise, pretty not far from the 2 degrees. That would cause a 4-degree average rise in temperature across the whole of Perth, increase of over 50% in extremely hot days, over 35 degrees, reduction in rainfall, and increased risk of fires. So this kind of leads us back to a little bit back to the kind of passive solar design thing, where you can lock in those sort of savings, and they will actually only increase over the life cycle of building as maybe thermal control becomes more important in 50 years or 20 years time.
That assumes you haven't designed your home for one climate and then it becomes another climate. I mean, if you've designed your home to today's climate and then it becomes 2 degrees hotter, then it's not going to work anymore, is it?
No.
So we should be designing our home so in that case we should be designing our home to have a heating requirement, not a cooling requirement. Wherever possible, we should be eliminating the cooling requirement.
In WA, yeah, definitely. Like, some of these scenarios.
Nearly anywhere would have to be. Like, you want to be eliminating the cooling requirement because that's only going to get bigger.
Some climates might. Are all climates predicted to get hotter? All zones?
It's like Australia.
It's the extreme weather thing, isn't it? Though, like.
So you might still have
you're going to get extreme storms or extreme.
It'd be interesting to model like a Kalgoorlie climate, but I'd be like modelling an X count. No, that's a bit.
Yeah,
looks to me like it's all going to get hotter.
Yes, only the problem. So would you be when you design your house, would you want to include more cooling into it?
What I'm saying is you eliminate the need for cooling. So if you've got a choice between say for example, you might have a trade-off where you say, okay, I can put this window in here, and that's going to make it warmer in winter, so I'll need less heating, but it's also going to make it warmer in summer, so I'll need more cooling.
Yeah.
And at the moment, that might be the benefit might be the net benefit of that situation might be due to the fact that it offsets more heating than it creates cooling, if that makes sense. So it might be a better decision to actually put the window in. But if you took into account the future grid, then potentially it's actually going to create more cooling demand. So I think that's intuitively that makes a lot of sense to me as well. I think that's the more tech. I don't know. Yeah, maybe not. I don't know. But there just seems to be this very easy way of supplying renewable heat through biomass, whereas supplying renewable cooling is much more technologically reliant on solar PV, etc., running the air conditioner, So, I don't know. There's two arguments to that story, but just intuitively, But that's just my intuition. We'd have to cut that out of the.
I think that's all I had actually.
Cool.
Yeah.
Awesome. Thanks, Pat.
No worries.
So, do you mind going back to one of the slides where you had comparison of different recommendations with different carbon intensities in the network? You mentioned Yeah, that one. You mentioned, you know, this sort of assumes that, well, the carbon intensity of the solar PV, because I'm guessing you have to assume a design life with this building to some degree, and then so there would be some replacement energy. But you also talked about the decarbonisation of material or products and materials as we go forward. So, you know, if the panel came from China or was heavily dominated by coal, then yeah, there'll always be a high carbon intensity with the PV. But it'd be interesting to model what happens if you assume decarbonisation of all networks under the same rate, because you could argue that China's actually accelerating faster than anybody in its uptake of renewable energy, and therefore solar PV from China might actually all come from solar PV run manufacturing plants, and therefore your embodied carbon is overall. And
yeah, so for PV, like that would probably tie in quite nicely, and you'd still just get the same sort of savings across the board. But that's because PV, the materials that go into PV don't have a huge impact. It's the manufacturing process of actually joining them together and making the panel. Whereas, like concrete is just a chemical process that's creating carbon rather than.
Isn't there a big component of heating for the silica?
yeah, there's now plants that like, I mean, most of the plants, there's a bit of a sales pitch, cover their roofs and solar PV and claim that X amount of their energy consumptions come from the PV, which is, you know, the same we do when we design a house and take PV on the roof. There's one in particular, it's the one that Infinite Energy sell, I don't know what brand name it is, but they claim to have a really, really high content of renewable energy input into the manufacturing process.
In the probably, yeah, but I would have assumed by far the biggest load would have been and that's probably still being done with coal and gas, I'm guessing. But
I don't know.
Well, we should check that out. It's going to be a reason.
Melting silica. What temperature does silica melt at?
I don't know, but it's in the iron ore up there, and iron melts at 1500 degrees or thereabouts. I would have assumed the silica is about the same.
Well, silica's quite a lot of, it's got to be pretty similar to glass, doesn't it? Isn't it? No, maybe not. I don't know.
It is glass, isn't it? Silica. It's
Yeah, it's what they use in glass anyway.
It's the purity of it all. It's literally SI.
But is that what glass really is?
Glass is silica, yeah, glass is silica.
It's a raw
And a few
element.
other bits and pieces thrown into it.
Yeah, and
I always
if
thought it was, but now I'm thinking, well, how can this whole silica shortage be?
it's the quality of it.
Yeah,
I'm pretty sure it's the quality of it. And it was a shortage because they had microchips, and then they
So
started.
this see-through crap is pretty low quality, is it?
I don't know. Now you're pushing me. I think it's what they then dope it with. So you get your sand melted down, and then you chuck other stuff in there to make it a silicon semiconductor.
Sorry, yeah.
But yeah, it'd be interesting to find out what else they can melt it with. And what
I think they use a lot of it's done with natural gas. I think.
there you
Gas,
go.
anyway.
Just do a quick Google, if you wouldn't mind that, for silicon cell manufacturing process.
The life of the solar panel is pretty short. It's only about 20 years.
25.
Yeah.
The recycling apparently is pretty, I mean, there's a massive demand for recycled silicon. Like there's good money in recycling your solar panels, so they're probably going to tell you all the technical stuff about how they dope the silicon rather than pure silicon, yeah. Silicon dioxide, cool. Electric arc furnace.
Okay, so there you go.
We might be okay. Don't need gas.
Yeah, cool.
Go solar! I didn't know I still was solar protecting. I think it's got a big part to play. That's cool.
Yeah, okay, there you go. Good stuff.
Mm.
Is an electric arc furnace 100% driven by electricity?
No, that's good enough. We're on the science is.
I worked for a couple of years over at Bradford's.
Oh yeah.
Well, now they smelt steel, typically scrap, and make gets with them. You know, the teeth on the bulldozers and things.
Oh yeah.
Okay. And they've got electric arc furnaces there for melting steel.
Bradkin, is that the same Bradkin that do the insulation as well?
No,
Different.
but I don't think so. It's a big company, but it might have brought into that.
Yeah. Okay, and so and they mix it with like and stuff to make it harder or whatever.
Oh yeah, they take samples of it and put it through like an X-ray machine.
Yeah.
It breaks down the particles and then says yes, you get so much of this and so much of that. And they shovel in a bit of this and a bit of that to balance it out.
Yeah, right.
But yeah, they're 100% arc furnaces.
And so it's just literally a big heating element that runs that.
No, it's arc. It's got they've got a big three-phase transformer at the back.
Yeah.
And they bring the electricity into some carbon rods of about this diameter.
Yeah.
And the three carbon rods go down into the scrap and generate an arc on that, and they just sit there like an arc welder, just like a big arc welder.
Yeah.
And melts it down. Yeah.
That's good.
Yeah, right. That's what they mean by arc. Yeah, right. It's actually literally, yeah.
It's like they say, it's just like a big welder.
Yeah.
Wow. So I guess the key will be how recyclable the panels become, because there's so much PV being put out at the moment, and with current installation levels.
It's only the surface of the silicon that's got the actual heat, the doping.
Yeah. But I guess when they recycle, I don't know whether they're going to be able to recover that. They'll probably just chuck it in back in the arc furnace and melt it all down and it's doping again.
And that's probably right here.
But whether that's a major component of the embodied energy is in the doping or not. I don't even know how they dope. They cut the cell and then you've got a cell and then
I don't know exactly how they do it, but my understanding is they build it in a tube with a rod about so 100 mils in diameter and however long they hit it, and then they slice it.
Yeah.
So there's got to be a certain amount that comes off on the slicing plate because it's like
yeah. Once they've sliced it, then they go do your doping.
Then they basically just build a lamp panel like you would with a circuit.
Right.
And then cut off the bits of the lamp that they don't want, then go from there. So it basically just builds onto the circuit. The silica is just an insulating base that you build everything onto. As the way I understand it.
The doping is, we studied it in engineering, it was the P and the N materials, silicon semiconductors. It would be interesting to see how energy intensive the doping is after you got your wafer.
Yeah, they build it like that and then cut off the wafers.
Yeah. What's the next stage after wafering? You dope them.
There you go.
So what are the traditional doping methods? Boron, phosphorus, and small amounts of there. Oh, the Kusach-Skarovsky process. So you've got to heat it again. Ah, right, okay. Back in, so there's a bit of energy there. So you get it back up and chuck some phosphorus gas in there. Particle accelerator, awesome. That's groovy, I like that one. That's Dr. Who material.
They can make them in Switzerland.
Yeah. It's not being accepted in commercial. Okay. So even if you recycle silicon, you still then, so you melt it down and mash up all your old recycled silicon, cut your wafers, and then you still got to get it back up to temperature and smack it with some gas. So would that furnace there be the same? It says back in our furnace, so that furnace could be gas. Yeah. Well, to get it up to 1400 degrees. That's pretty toasty.
1400 degrees, yeah.
It's very toasty.
It's probably
Have to be super clean though, I'm guessing, that furnace.
Well, it actually says the presence of phosphorus gas, so almost like it deliberately burns.
Well, that's to get the doping in there, the phosphorus doping, but you'd have to be super clean and controllable to get that process.
Yeah, the particle accelerator hasn't actually
got underway.
But, that's
the future, man.
Yeah, well, probably is, probably right. Yeah, it's pretty.
Yeah, we really.
The same thing will also happen with carpet.
Yeah.
So
all the materials become carbon
intensive. So I guess the key thing is that is you want anything that's going to create a saving today should maybe have a higher weighting. Yeah, because we've assumed that the materials impacts over time don't decrease either, haven't we?
Yeah, that's what I was asking about remodeling with a decrease in carbon intensity materials. Those that can be decreased, and that's what you were saying, that some materials will never be able to, like wool. Oh, I don't know, they're talking about getting sheep that don't burn far, so maybe we'll see a decrease in carbon intensity in wool carpets.
They've already tried some of that, because kangaroos belch sulfur.
Right.
They got a different gut biology than sheep and cattle.
They're not ruminants.
Well, they are. They don't. They've got a different. The bugs in their gut is different, so they actually belch sulfur dioxide or something.
Right.
It's a sulfur-based gas.
Yeah.
Which is not a greenhouse gas. So what they've tried doing now is to genetically modify sheep and put this bug in their gut. But apparently it didn't work very well.
I feel sorry for the sheep there. Yeah, nothing worse than having uncomfortable guts. Nothing worse than being a sheep with kangaroo guts.
I thought you were going to say that cloning study. That would have been interesting, saying sheep and a kangaroo.
Yeah.
The new meat merino.
Yeah, meat merino.
That's like a wallaroo. Wallaroo's kind of long.
Yeah.
Interesting stuff.
Like a sheep. Yeah, cool. I have to shoot off, mate. Did you mind giving Ian a quick overview of software?
Yeah, go on.
And then I might have to pull it down and see how it really goes.
Yeah, go for it.
So this is the platform. It's all kind of web-based. Yeah. It's all web-based and free. So, like, if you're interested, we give you a login and just go online, and then you've got to get your platform set up, kind of like this. These are all the kind of projects that I've had going on over the last few years.
Well done, Pat. I'll catch you tomorrow, mate.
Cool.
I've got a meeting tomorrow morning first up, but I'll be in after that. Nice to meet you, Ian.
Yes.
Catch you later. Thanks, Pat. Yeah,
Thank you
thanks.
very much for what you've done.
So I just drew into like an example. This is the one I was actually working on for the presentation. So here we have kind of three key elements of a building: the assembly, so the labour and equipment that would go into the building, the materials, and then that's split out into finishes, fittings, floors, foundations, landscaping, etc.
So where do you actually start?
This is where I would start. So at the moment, it's actually let's just go from scratch, shall we? Why not? So we have different levels. So this is like a project level. I could put different buildings and different structures and different design options into each into this kind of project. So there's some kind of master information that I plug in here, which is my postcode. This is the database that we use. This is the different grids. So we've actually got a whole heap of regional grids and worldwide grids, and more recently these future kind of grid scenarios that we're talking about today. We've got gas and water grids as well. So that would be kind of master information that feeds through into all the designs that you might be looking at. And then you get into this kind of structure. So this is just for a specific address, and then in here I might put different design options. These are all my different kind of design options.
So basically you take the design and you work out how much steel it's got in and how much concrete it's got in and et cetera, and key that into the system. Is that what you're saying? Yeah.
Yeah. So
Great to meet you.
Yeah. Thank you, mate.
Catch you tomorrow.
yeah, so here's the actual building, and jump into walls, and I'd say add walls, and then I've got all sorts of different materials, and in the back end of here there is all the life cycle inventory data that goes into the materials, so all its transport impacts, its manufacturing impacts, it's all sort of stored in the back end. So I've just put, say, masonry bricks, anti-clay brick, you can have recycled option there, or just normal. Or something, and then we can put it in kilos, or we can also put in the dimensions of the brick and then calculate that. So
it goes through and calculates it all for you.
Yeah. So and then what's the standard brick? 110, 90, and 70 or something, and then you might say, oh, I've got 200 bricks, and then it gives you all the kind of answer there. We also put in the material lifespan, so brick is probably going to last
probably 100 years.
100 years or so. We have a reference library here as well, so if you are interested, you might be able to look up life expectancy, and we have a few things like references there if you're not sure. It's kind of industry standards for materials, but yeah, 100 years sounds reasonable. And can actually scroll down here. That's interesting. Because I'm stuck on the projector. That's basically the bottom, and then there's a little OK thing.
Okay, so
I can't get to it. That's really weird. Oh no. Terminal. There you go. And then save that. And then we have the brick, quantity, its life, and then this is its life cycle impacts over the life of the building. Now you could do that for every single.
So what are you saying? That the 83 is what's it?
That's kilograms of CO2 for the life of the building.
Oh, okay.
Yeah. So
the idea is to get that down as low as possible.
Yeah, this is the figure that we're worried about. Although, if you are interested in another impacts like water or ozone or toxicity, we have a whole range of other ones. So let's just have a look at water. Interesting. So then you've got impacts from water, so that's kiloliters. So to manufacture those bricks took 4 kiloliters of water as well. It gets really interesting actually when you look at things like human toxicity. So people, when they think about human toxicity, they think about using non-toxic paints and things like that. Well, actually, the paint doesn't have a huge impact on the life cycle of the building. The toxicity is all in the electricity that's going into the building. That's the impact.
PVC insulation you're talking about.
These are all toxic elements, but the toxic element in the coal and the gas that's happening in your environment, that's the.
So if you look at electricity as an example,
we'll go back to CO2.
Okay. I mean, the problem is that the bricks you probably use some sort of electric furnace to heat them up and cook them. But
So we could do that for every single material that's going into the building, and that would be quite a laborious process just to run through that. So what we have is templates, and we have this library where we've taken, say, a metre squared of wall, added the mortar, the bricks, the damp-proof membrane, the assembly, the labour that's gone into doing those bricks, and building the wall up. We built it all up from scratch for a metre squared, say, and then we can add just the actual area of wall that we've got in. So we've got different types of brick walls, different types of finishes, foundations, if it's insulated.
So you get so many metres of certain wall.
So we have a cavity wall there, for example, and then 100 metres squared.
Yeah.
And that's
the calculation for it.
Okay. So in here, I've got in the walls. I've already got a single brick wall. I've got a door. I've got the windows. It's all built up in our template library, which makes things a lot easier.
Yeah, I can imagine.
I jump into assembly there as well. That's quite interesting. This is all the construction assembly. So the sort of run time of different equipment, your concrete pump, and then tradies to come to site and run the pump. This is the sort of time that they're spending on it, and the impacts that has on your car. And what we've also got costs in there, which at the moment it's not something that you would sort of cost out your whole build on, but it gives you a general feel for where the costs are coming in. And labour's always interesting on that one because it's the labour costs of the builds that really kind of add up.
How do you actually go about getting those sort of figures?
So a lot of it's referenced. We use Rawlinson's, which is a kind of quantity surveying textbook, basically.
Okay. I was going to say, if you went to BCG or Bookmakers or something, it says, tell me what the cost to make a brick, they're going to tell you to go somewhere.
Yeah, exactly. Yeah, they're like, people spend all day phoning up people and getting quotes and costing jobs. We haven't done anything like that. We've taken the kind of industry averages from, it's called Rawlinson's in Australia. There's another one in America called Spons, I think it is.
Oh, okay.
It's just a big textbook, and it's full of like dollars per meter or dollars per hour
or whatever,
for whatever material or labour that goes into the build.
And the breakdown of all of bits and pieces. A brick has got this much clay and this much.
It's just a cost textbook. It wouldn't go into that sort of detail. Yeah, the data for that would come from manufacturers usually.
Yeah.
We try and get it from.
Anyway, I should go, I suppose. You want to go home as well.
If you drop us an email, we can set you up an account and you can have a little play around. There's loads of like online videos that we've done that sort of lead you through the kind of process for building up your own LCAs if you're interested. These are all the templates that have gone into this one, so it's pretty extensive.
Mm-hmm.
And the it's interesting actually. This has got we're still on cost. So you can see here on this pie chart, you've got your recurring costs, and product costs, construction, and actually energy is quite small. And the life cycle of the building cost of energy is relatively small. If you jump back into carbon, actually products is fairly big there as well. And energy jumps up to 22%. I think in here I have because I was modelling that solar panel example, so I've got 3 kilowatts of solar PV on this house, so their energy is pretty much halved because of the PV.
Well, that's going to be interesting because I can't remember what the figures are now, but I think it's 5 kilowatts if you could connect it is the maximum.
Yeah, it's 5 kilowatts is probably allowed on a resi system,
Mind you, that's probably not too bad. 5 kilowatts is probably what the average house uses anyway, so.
5 kilowatts is probably what the upper side of what a normal house is, unless they've got a swimming pool or something like that. Yeah, certainly. If you're looking at an apartment, we do a lot of work on multi-res and apartment blocks, and they're having kind of 2 kilowatt systems, and that brings them fairly close to operationally neutral. Can you jump into your operational? You can see the sort of things that are making up your operations. So that's your heating and cooling, hot water, refrigeration, kitchen appliances, laundry, and then your entertainment, which is the appliances. So it really helps you to kind of focus on the big things. There's a big focus in BCA about reducing your thermal requirements and getting the 6-star thermally performing house. And there's no mention at all really in the building codes about what you use for your hot water, when in fact your hot water now is taking up a lot more of your carbon and your energy.
Yeah. In fact, it would be interesting to model, well, I find it interesting anyway, to model the difference between, say, an electric storage hot water heater and instantaneous water heater. Because I suspect an instantaneous water heater will be a lot more efficient.
Yeah, they are. And I'll jump into the library here because we've got them both up. So electric. And what was it? Storage.
Storage, yeah.
Yeah, I don't remember what we would call it. Let's just do electric and see what comes up. There we go, storage, 160 litres. So we can jump in here, and we've actually, in most of the templates, we've got in the details here, and we've got how the template was built up. So a whole heap of detail and calculation. This one is actually quite extensive because it's hot water. In, you know, what's your demand for hot water, how much hot water is being used, how that relates to your occupants, tank losses, and then what climate you're in, and all these sort of factors are taken into account. But in terms of energy, I'm in the library here, so it's assuming there's like 100 occupants or something, so this is looking quite large, but you're on 44 million there, whereas instantaneous, you're on 40, so about 10% saving because of your losses in the tank, basically. In
the apartment we're living in, it'd be a hell of a lot more than that because the hot water cylinder's on this side of the apartment and the bathroom's on that side of the apartment.
Yeah, it's
and the copper pipe goes straight across in the concrete, so we've got to heat up all this concrete before we get hot water.
Yeah, it's probably not insulated. Is it the pipe work? Or?
No, it's not, because we had a leak just recently and the guy came in to fix it. And it's just a bare concrete, just a bare copper pipe sitting in the wall.
Yeah, and it gets even worse when we're working on like 20-story apartment blocks and they've got ring mains running around the whole apartment block and all it's doing is heating up the space.
Yeah, that's right.
And like you just need to put some insulation in there and you can get cheaper hot water and less cooling requirement in the summer, you know. Yeah, that's a 5-minute flash.
That's really good. It gives me a good overview, so I know basically what I'm looking at. So that's that's good. Yeah,
there's a few videos that can take you through. This is the details tab. So in here, I put in a predicted design life. We have a few algorithms to calculate that based on your postcode and stuff. If you're not sure.
But that wouldn't make a lot of difference. Excuse me. This will be the boss. Hello. I'm just coming now. So if you come around, I'll be downstairs waiting for you. Yeah, as I say, if you drive around. Right. Yeah. Okay, I'll do that. Okay. See you. Sorry about that.
No worries.
She wants to go home for dinner. Well, thank you very much for that. That's really good.
Pleasure.
I'd like to keep in touch with you. How are you going with your power grid as well?
Yeah, it's a tricky one. It's a tricky one. So, yeah, because we're always like the problem now at the moment is the coal basically reverse it. At the same time, we've got
part of the government. This government department, like we're going to do. You've got to mix the government, they need to do something about that.
yeah.
All right.
Cool, okay.
Thanks very much.